wanted to spend a few minutes to talk about electromagnetic induction and talk about Faraday's law for electromagnetic induction. The reason I wanted to talk about electromagnetic induction and Faraday's law of electromagnetic induction is that at first sight, Faraday's law looks simple, and when you look into it deeper, it looks very puzzling. The reason it looks simple is that the equation itself, the law itself, is simple. The equation or the law says that the induced EMF in this phenomenon we call induction is in proportion or equal to the negative rate of change of magnetic flux. So that's a simple law. What's puzzling, what's complicated, is that there are two types of electromagnetic induction. One is called transformer induction, and one is called motional induction. In the case of transformer induction, the cause of the changing magnetic flux, which produces the induced EMF, is a time-varying magnetic field. In motional induction, the cause of the changing magnetic flux, which produces a induced EMF, is a moving circuit. So it's very strange, it's very odd, are both described by exactly the same law. They're both described by Faraday's law. In addition, Faraday's law, while it's simple and straightforward, induced EMF is negative rate of change of magnetic flux, it doesn't really tell you, it doesn't really inform you of why a changing magnetic flux creates a induced EMF. And in particular, it doesn't tell you why a changing magnetic flux in the situation with a moving circuit creates an induced EMF, and why a changing magnetic flux in the case of a time-varying magnetic field creates an induced EMF. So here's a summary of the situation. We've got a simple law for an intriguing phenomena. Within the simple law, there are two effects: the case of motional induction, the case of transformer induction. And the simple law really doesn't tell us how motional induction works. Why does the changing magnetic flux in that case create an induced EMF? And the simple law doesn't really tell us in transformer induction why the changing magnetic flux creates an induced EMF. And so I want to say a few words about the heart of the law. I want to say a few words about what creates, what causes, what's the mechanism for the motional induction? What creates, what causes, what's the mechanism for the transformer induction? To answer this question, let's think a bit about what induction is, what this induced EMF, induced current, actually is. To help us, let's imagine the induction in a loop of wire, a thin loop of wire. It could be a nice circular loop, it could be a simple rectangular loop, or it could be any shape of loop. So I've sketched a loop of wire here. Inside the circular, the square, the honey-shaped loop are ions and electrons. There's metallic ions, positively charged, and negative electrons. Now, the positive metallic ions are fixed in place in the wire loop, but the electrons, or at least some of the electrons, are free to move around the wire loop. An induced current from an induced EMF is the movement of those electrons, is the collective flow of those electrons around the wire, around the circuit. Those electrons might flow clockwise, they might flow counterclockwise, but there's a collective flow of electrons in this induced current. So what is pushing the electrons around the circuit? What's causing the electrons to flow around the circuit? What's causing this electrical current in the circuit? So how can we drive the current around the circuit? How can we push the current around the circuit? How can we drive these electrons, push these electrons around the circuit? There's two ways we can cause the electrons to flow around the circuit. The electrons, being charged particles, will experience a force, an electrical force, in an electrical field. That's one way. An electrical field could push the electrons around the circuit. The electrons, charged particles again, if they're moving, we've got moving charged particles in a magnetic field that also will create a force on the moving charged particles, the electrons. So that's another way that we could push electrons around the circuit. So to summarize that, there's two ways that we could induce a current in the circuit. We could cause electrons to flow around the circuit, and one arises from a push that's conveyed by an electrical field. The other one is a push that's conveyed by a magnetic field. And that's very interesting because we can think of motional induction as arising from the push due to the magnetic field in the neighborhood of a circuit, and the push on moving charges in a moving circuit. And we can think of transformer induction as the push from an electrical field in the neighborhood of a circuit. It would push the electrons around the circuit. So the punchline is that when we think about motional induction, we think of it as an induced current that is created or produced by a push from a magnetic field. And when we think about transformer induction, we think of it as an induced current that's created by a push from an electrical field. So they truly are within the law of induction, within Faraday's law of induction, that the induced EMF is in proportion to the negative rate of change of the magnetic flux. There really are two ways of causing an EMF, pushing a current around a circuit. And one is actually magnetic in nature, and one, perhaps surprisingly, is actually electrical in nature. Emotional induction, the discovery that the push of the charges in the circuit that create the current in the circuit is due to moving charges in a magnetic field, is kind of a ho-hum explanation of motional induction. It's an explanation of motional induction in terms of a very familiar magnetic force on a moving charged particle in a magnetic field. In the case of transformer induction, the fact that the push on the charges in the circuit is due to an electrical field conveying an electrical force is actually revolutionary. It's groundbreaking. It's transformative. Emotional induction, we've actually discovered nothing new through motional induction. We've just revisited the magnetic force on a moving charged particle in a magnetic field. In transformer induction, we've discovered something completely new. We've discovered that a time-varying magnetic field creates an electrical field, and that's pushing the charges around the circuit. Later on, it was also discovered that also a time-varying electrical field creates a magnetic field. And so there's a pair of inductions, electromagnetic inductions, in which either the magnetic field, if it changes in time, creates an electrical field, or if it's an electrical field, it's electrical field varied in time, it creates a magnetic field. This is a completely new world. in the past, we've talked about charges creating electrical fields and therefore electrical forces. We talked about moving charges creating magnetic fields and therefore magnetic forces. But now we've got time-varying magnetic fields creating electrical fields. That's amazing. We've got time-varying electrical fields creating magnetic fields. That's also amazing. This is a new world in which not only can electrical charges create electrical fields, and moving electrical charges create magnetic fields. Time-varying electrical fields can create magnetic fields, and time-varying magnetic fields can create electrical fields. We've got 4 ways now, not 2 ways of creating electrical magnetic fields. One through charges or moving charges, and another one through time-varying electrical fields and time-varying magnetic fields. This was revolutionary. This was groundbreaking. This is the beginning of electromagnetic. In Gauss's flux law, which I've written down here, we're asked to think about, we have to think about, a closed surface, a surface in which there's a definite inside and a definite outside. And the flux law, Gauss's flux law, tells us that the electrical flux through the closed surface is in proportion to the charge that's contained inside the closed surface. So phi here is the electrical flux through the closed surface, and Q here is the charge inside the closed surface. Now, the flux law, Gauss's flux law, is just an alternative description of the 1 over r squared proportional to charge electrical field that surrounds every individual point charge. However, Gauss's flux law is important, useful, because it's a new way of thinking about charges and the fields that charges create. It's a way of thinking about charges as sources or sinks of electric flux, of lines of electrical field. And it's also important because it's frequently a handy tool, a very useful tool for solving problems involving electrical fields and electrical fluxes and electrical charges. In Faraday's flux law, it's written down here, we're asked to think about an open surface, not a closed surface. It's a surface that's defined by a loop of wire or an electrical circuit. It's the surface within the loop of wire or the electrical circuit. And the flux law, Faraday's flux law, says that the rate of change of flux through the surface determines the induced EMF that will push charges, push currents around the bounding loop of wire, the bounding electrical circuit. So in Faraday's flux law, over here on the left-hand side, we got the magnetic flux, and we've actually got the negative rate of change of the magnetic flux. And then over here on the right-hand side, we got the induced EMF that will be associated with an induced current around the electrical circuit. In motional EMF, Faraday's flux law is again an alternative way of expressing or understanding that a moving charge in a magnetic field experiences a magnetic force. The moving charges in the electrical circuit that we're thinking of in Faraday's flux law, in motional induction, those moving charges in a magnetic field experience a magnetic force, and that causes them to be pushed around the circuit. It causes the induced current, causes the induced EMF. So in this case, Faraday's flux law is an alternative way of expressing the magnetic force law on moving charges in magnetic fields. The flux law is very handy in one way because it's a tool with which to solve problems involving moving circuits and magnetic fields. It's a new way of thinking about moving circuits in magnetic fields that allows us to solve those problems. If we can calculate the rate of change of flux, we can calculate the induced EMF and the induced current in the circuit. But Faraday's flux law, unlike Gauss's flux law, holds a surprise. Gauss's flux law is simply a different representation of a description of the electrical field of an electrical charge. Faraday's flux law in motional and induction is also just a different representation of the magnetic force on a moving charge. But Faraday's flux law held a surprise. The surprise was a new phenomenon. The new phenomena, the new effect, was that a changing magnetic field also creates an induced EMF. That's a completely new thing. That's a completely new effect. Now, you might wonder, you might question, how could it be that one law, Faraday's flux law, describes two different effects, describes two different phenomena? One of them is due to a moving charge in a magnetic field, and the other one is the effects of a time-varying magnetic field creating an electrical field. Those are two very different effects. How could one law describe those two very different effects? Well, the answer is we just understand that it's a coincidence. We just understand it as an accident, that one law, one equation, especially one simple law, one simple equation, is describing two different effects, two different phenomena. There's nothing deeper about it. There's no conspiracy about it. It just happens that in this case, this particular case, one law describes two effects.